Our last speaker of today will be Hainzl from LMU Munich, and he will talk about bosonic features of fermionic systems, high and low density Fermi gas. And I just would like to let you know that if you write something on the blackboard and you cannot see it, please unmute yourself and let us know, because then we try to change the technical setup. So I'm looking forward to your talk. It's great to see you.
Okay, thanks a lot. Thanks a lot for inviting me to the nice place here. So this is maybe the first conference where I'm the most senior speaker, which is a little bit shocking.
On-site speaker.
The most senior on-site speaker. So and since I'm here the last speaker, I have somehow the duty also to tell younger people what would be nice problems to work on, and therefore I should really do that. So I really want to say something general. Before doing that, let me just say that somehow the content of this talk is basically given by joint works. By one joint work with Martin Christensen and Nam, and this is about basically the same model as Benjamin talked about before. So he did basically half of my job. The difference is that we use a really different approach. So when we started this work 2 years ago, our goal was very ambitious in the sense that we want to cover also not mean field regimes, but somehow we could only do rigorous proofs in this part, so now we are back to that. But I think the one advantage of our approach is that it takes us a little bit closer to the physics, and that's why I really want to restrict here my presentation more to the physical picture, and I will not go into details of the proof. And then I will also, parts of that also covers joint work with Marco Fanconi and also Emanuela and Marcello, and also some ongoing work. But I will not say so much about that. So now let me start with something, let me basically say something general. And now I put here the title in kind of Revolution in Mathematical Many-Body Quantum Systems. So last week I was taking the train from Vienna to Munich, and there I read an article from David Heinz when he especially talked about his work about this random phase approximation, basically what Benjamin was basically talking about before. And this was interesting because he described that in retrospect the work he was doing with Bohm was a paradigm change in theoretical physics. So he basically describes it that till then, the people tried to do somehow a top-down approach, meaning that you basically look at your constituents, you identify the forces between them, so the potential, then you write down a first principle Hamiltonian, and you just try to attack it as good as possible. Now, the time when Heinz started his work, thinking about electrons in metals, one was at the point that one did not understand the behavior of electrons in metals, in the sense that the experiments didn't coincide with the theory. Because till then one usually had a theory, Hartree-Fock theory, and that did not explain the specific heat of metals or the cohesive energy. And the problem was that usually the standard methods to go beyond Hartree-Fock was perturbation theory, and the perturbation theory failed. And therefore, basically, they came up with a different description. And actually, and in retrospect, he says, from that point on, one changed. I'm not allowed to walk here.
You can walk there.
Okay. So the paradigm didn't change from his perspective was that from that time on, one started to basically describe emergent phenomena. So in the sense that so his description, or their description of metals was that there is a collective behavior of electrons, what they call plasmons. So this is a kind of oscillation of all the electrons together. And so they had to somehow, from a let's say, from a classical point of view, they translated this into the quantum picture, and they somehow separated this plasmon behavior from basically quasi-electron behavior. And his view of this emergent paradigm was that now, from that point on, one tried to use experiment to guess what are collective behavior, like Bose-Einstein condensation, superconductivity, and then tried to, by phenomenology, to identify the organizing principles. And basically then try to discard the parts of some Hamiltonian which you expect do not contribute, and restrict your attention to the important ones. And I really want to describe that in terms of the Fermi gas. But now I think we are at the point, and maybe the problem from that time on was maybe that mathematics and physics kind of didn't talk to each other, because usually when you think of as a mathematician as a problem, you look at a physics book and then you basically don't understand anything, or you cannot really put that together with what you want to prove yourself. So therefore I want to make a commercial to what actually Benjamin was also telling us before, that now we might have methods in mathematical physics where we can reconcile this picture. In the sense that you really mathematically guess what should be the right structure of, for example, the ground state, and then prove things rigorously. Okay, so what do I want to say? I want to say that this kind of unitary type rotations, which were presented before by Benjamin, open up a new way to deal with many body correlations. And this holds for bosons and for fermions. So now, and in that respect, so let me say, so I added here a few names, beginning with Hepp and Schlein-Rodjansky and so on. But I would say, I think the big benefit to bringing attention to this kind of methods goes to Benjamin. And so he basically, maybe using ideas of Hepp, he used kind of, how do you call that, Y transformations and also Bogolubov transformations to basically perturb around some kind of state you're interested in. And in particular in the work with about bosons, together with Boccato, Brennecke, and Genatiempo, so he introduced these Bogolubov rotations to really show Bose-Einstein condensation and also the excitation spectrum. So now let me say that for things like bosons, of course, we had great fundamental works before. I mean, starting from Dyson and over, of course, Elliott Lieb, Robert, Lieb and Robert first and foremost, and also Jan Philipp, and also others. I mentioned just some names, but I just want to say that these works are not so close to physics as it is now for the Bogolubov transformations, because this is closer to what you find in physics books. Now I just want to say, if you look at the works, then the advantage is, as I said, it's closer to the original physics, and it's conceptually simple. This is maybe the most point. If you look at some of these papers, you may think, oh God, if you see hundreds of pages, then the problem is that you need many estimates. But I would say over the time, I think one can simplify these. But what I want to tell now the younger people is that I think that these methods can be really generalized to other systems. So I would expect that if you, for example, study phonons, or also superconductivity, maybe even quantum Boltzmann. This is just a guess that these methods could really help, and that's why I basically would ask anybody to try to give it a shot. And so now let me start. So after this general introduction, I just want to start with talking about the more specific and talk about this somehow Fermi systems. And now let me introduce here. So I want to talk about, so for example, when you open Feta-Walecka, then two important systems, what they call is a degenerate Fermi gas and an imperfect Fermi gas. So one of them describes a high density Fermi gas. Now, this wonderful picture I put here should mean you look at the metal, which has a uniform background here, and then you see these red points here should be electrons. Now, if you imagine they're interacting with Coulomb systems, so this describing electrons in a metal, then basically when you open up a physics book, then you will see some kind of picture which describes Feynman diagrams. And these Feynman diagrams are nothing else than doing perturbation theory. So when you and of course when you do very general Feynman diagrams, then you get many. But now I want to show you that in these basically two different systems where you have a high density and a low density Fermi gas, they kind of organizing principles to recover the most important features of the ground state are just given by selecting the right diagrams. So for example, by electrons in a metal, when you look in, let's say, I don't remember actually which book I have that from, but if you look at here the ground state energy, then the first thing here is just the kinetic energy of a filled Fermi ball. So now thanks to Benjamin, I don't need to explain to you what the Fermi ball is. So you still have the free Fermi gas, which you fill here completely. The first part here consists of the kinetic energy, and that is just this diagram just represents the first order perturbation theory, namely the direct energy, the density-density interaction, and this is the exchange term, which because they are fermions. Now, if you do second order perturbation theory, you get here two other diagrams, and so you see these little things here. So if the error goes down, then this means that this is a hole, and if the error goes up, this is a particle. So basically, this describes. So you have to think of that. You start with the field Fermi C, and then you get the hole here and an excited particle. So you get the pair. So this is what this bubble here describes. And for example, this diagram you can think of that you have two holes here interact with each other with the potential V, then two particles jump out, and afterwards these particles jump in again. So this is for example one diagram, and the other diagram, which is because they are fermions, you can jump back in the other hole. So this is one way to describe these diagrams. Now, what I here want to say is that when you look at the physics books, then you really say, okay, now for the electrons in the metal, all these kind of bubbles are the main diagrams. And so what Gell-Mann and Bruckner did in describing, they were basically after Baume-Pines the first who described the ground state energy to the leading order correctly is they were summing up all the diagrams. And they ended up at an expression which is similar to what Benjamin already showed us. The interesting thing here is that each of these diagrams, each of the ones, if you write it down as integrals, diverges, each one. But the statement was that if you sum them up, then they are finite. And and you see, this is the reason why, for example, second order perturbation theory didn't work, because one of those is really divergent. But miraculously, if you sum them up, then they're finite. So now, if you look at the other side of the picture, you can see here less particles. So if you look at the low density Fermi gas, for example, something where the particles are repulsive, this is a model which is used in nuclear metal, then of course, although formally the Hamiltonian is the same, you just have a different interaction potential, but since they are less and they are repulsive, the idea is that the scattering is the most important part for the ground state energy. And so in order to recover the ground state energy, if you look in a physics book, then you have a totally different type of diagrams. So now what do these diagrams here describe? So first of all, you look at low density. Low density means that the Fermi ball is smaller, significantly, because that goes to this is just proportional to the density of the particle. So now, what are these diagrams describing? These diagrams are describing that, for example, you have the two particles here inside interact. So now they jump out, you have two holes. And now they are scattering with each other, and then they go in again. That's actually this picture. And you have two ways to go in again. Either they go in the same hole, back in the same hole, or they exchange. So now what I want to tell you is that the organizing principle for the physicists is you look at the corresponding diagrams, you choose those sort of diagrams which you think contribute, and you calculate. And our duty is now to make that rigorous. I mean, to find a way how to represent this in a rigorous way. Okay, so now let me be more specific. So I put now here a Hamiltonian, which is the same as Benjamin presented before. So I do not yet write here. So later on for the high density, I choose here mean field. So I replace it by V hat of K and Kf. So by the way, my Kf, when I talk about Kf, this is proportional to n to the 1/3, just as a reminder. So this is just the Fermi momentum. Now, so this is the Hamiltonian, so I don't need to say much about it, but now the goal is that one has to decompose the Hamiltonian so that you can recover these two different pictures. I mean, you have to recover two different pictures, and that's what we want to do. So let me first rewrite this Hamiltonian in by just putting the A here on the other side. And doing that, we get one commutator, which gives me the n, but what I can do, I can write the other interaction just as rho star k rho k, and rho k is just this here, where here you sum over the momenta of basically two an annihilation and the creation operator. So if you put here 0, then you have 0 here, then this is just the number operator. And since I do the same as Benjamin before, we just fix the number of particles and we assume that the Fermi ball is filled. I can treat that just as a number. So the next thing, so the only difference to what Benjamin is, I do not this particle Hall transformation, but I do something equivalent, namely I assume, for me the ground state around which one has to perturb is the field Fermi-C. So I think of the field Fermi-C, and everything is one calculates relative to that. So I also want to extract here the Hartree-Fock energy. So I did not write Hartree-Fock, I write free Fermi-C, so free C. So this is the energy of the free Fermi-C. So this is the expectation value of this later determinant where the Fermi-C is filled. So now I extract basically the sum over p squared for p smaller than kf. So basically for all particles inside the Fermi-C, and doing that, I just turn here the sign round and write this as a star. And what I also can extract is here the k equal to 0. If you have rho 0, then this is just an n square. So this is extracted here together with this n. This is just n times n minus 1. And then I also extract here the n, the sum over k, but not totally, only part of it. So I will come back to that. So this Lk, this is this part. I will come back to that. I'll show you a picture later. So now I want to rewrite this Hamiltonian here in such a way that you really can basically distinguish, that you really can somehow get a guiding principle, which is the more important term for representing these parts or representing these parts. Okay, so now let's come back to the density operator. This is something Benjamin did also already before. So this part, I think Benjamin wrote the plus, and he also had, I think, AA or A star, A star. The only difference is that we do not this particle Hall transformation. So I can decompose this P in a part where P is outside the Fermi-C and P minus K is inside the Fermi-C, or something just the opposite, that the momenta are inside the Fermi-C and P minus K is outside the Fermi-C, and of course the parts where both are inside and both are outside. And so now I just describe the one here by bk and the second one by b minus k dagger or star, as if you want. And actually, so one of the big differences to what Benjamin did before, so we do not use this part here. We will not use this part as kind of a boson, but we simply only use a pair. So basically you have to think of, so now let me write this like that. So now I only think of pairs where I annihilate a state with momentum p and create a state with momentum p minus k. So when you look at the creation operator, then what are you doing? You always have to think relative to the Fermi-C. So you create the hole here. What do I want to say? Yeah, so you create a hole here with momentum p minus k, and you create a particle here with momentum p, which is outside. So now the most important thing is that this pair, since one is inside and one is outside, they satisfy these relations, and in some sense they also almost, I mean, this almost here has, of course, to be defined carefully, somehow fulfill the Bosonic bosonic creation and annihilation operator. In that sense, one can think of that as bosons, and you have to think of that if you apply this on the full Fermi seed, then this is of course 0. So now I think I have here a kind of a picture again. So this B star, with this P, so for P you create the particle here outside, this is the momentum P, and all is for a given K, so you can think of this is actually this here is my PF, so this is the Fermi ball, and this part is the shifted Fermi ball by momentum K. And what I denote always as LK, this is just this loon here. So again, if you create here a pair, you create one particle with momentum P, and then you annihilate the whole here with P minus K. Okay, so now let's come back also to the to the kinetic energy. So as Benjamin similarly said before, now you can think of, so if you look at the commutator from the kinetic energy and one pair, what you get is, you get here this excitation energy of a pair, which is P squared minus P minus K squared on this times the creation operator. So this is equivalent to saying that you can represent almost this kinetic energy just by this operator, where you only sum over pairs, so where you have a diagonal operator summing over pairs, where each pair has this momentum. So now just think a second, what does this momentum mean here? So you have to, now I usually wanted to make a picture at the blackboard, so now let me make a picture here. So think of what does this do. Think of, you have here your full Fermi seed, then you create the hole here with momentum P minus K, and you create here a particle with momentum P. Now what is this here? This is just the difference of the kinetic energy of this picture minus the situation where you have a full Fermi seed. Yeah, so so the difference from this picture to that picture is just that you created here a P and you had a hole here. So you add here the P squared, the kinetic energy of this particle, minus the P minus K squared, the whole of that particle. So that's how you can think of the excitation energy of a pair. And now we can rewrite the whole Hamiltonian by taking out the Fermi energy. Then the kinetic energy H0, which is the same as Benjamin called H0, and then I subtract this term here, and I add it. And this is exactly as Benjamin said before, this part here can be considered as small. So now you are left with the rest of the Hamiltonian, and what I did here, I just replaced here rho by these terms and plugged in here. So now you get different terms, and now you can say, okay, now if I look at the high density Fermi gas, then the picture which I see in the physics books tell me that this is the important part, and I can basically try to analyze this as good as possible and estimate the rest. And when I look at this low density Fermi gas, where the scattering is the most important part, then I will see that I need to take this one and I need to take parts of that one. Okay, so now when I write here lambda k of p, this is just this excitation energy of a pair. Okay, so now I wrote it again. for the high density, I identify an effective Hamiltonian like that. This is just as Benjamin did before, just using maybe a little bit of different notation, and not yet doing here the mean field approach and keeping it general, or the low density scattering, where I now have this part, and I have that part. So, and if you know a little bit about bosons, and if you do commutators with B's, you see that this term here behaves as if it would look like that. As if it would really look like a quartic operator where you have B star, and BP. And then you can say, so if you know if you know about how to basically deal with the Bosonic operators, then you can use ideas now to basically extract the scattering properties from this Hamiltonian. Okay, so now let's come to the high density. So as before, so this is the effective Hamiltonian. If these were only bosons, you can diagonalize this exactly. So now the difference, the conceptual difference to before is we really treat this as a pair, so we do not need any patches. So basically we can fix this case. Actually we look at k and minus k, so we combine them, but that's now not so important. And then you can diagonalize this basically for each k, and you end up with an expression like that, where this term will be the correlation energy and will be similar to what we saw before as the correlation energy. And then you have a matrix Ek, which describes the excitations. So this is for the effective Hamiltonian. So maybe let me just tell you for a short minute what this E of k and this Hk is. So this, so now I made here a picture. So this Ek or Ek square is isospectral to a term like that, where this Hk is nothing else than this lambda k piece, and this is just the excitation spectrum of a pair. So you put this on the diagonal, so this is the operator Hk, which is a matrix, and it is a matrix, so the number of basically points in one of these looms. So the second part, so here is a projection. I mean, this is now not so important, but it is important if you want to see what the eigenvalues are. This is basically a projection where you have only ones, and here the potential. So you can write that as this, which is a projection on this kind of vector. But this is in the moment less important. Okay, so now let's come to the main theorem of the result together with Martin Christiansen and Nam. As I said, the model is actually the same as Benjamin presented before. We also look at the mean field. We have here the same condition on the potential as before. And under this condition, we can say that the infimum of the spectrum is given by this expression. This is just the energy of the free Fermi sea, like before. Now, this here represents the correlation energy, and this is proportional. This is proportional to Kf, so to n to the 1/3. And for that, you have to remember that in Benjamin's notation, before doing everything, he multiplied everything by n to the -2/3. So therefore, it's really in that sense a similar result. Except that expression looks a little bit different. So now let me just say something like that. So first of all, in our work, of course, we can quantify that depending on the fall-off of Vk, but this is something I don't want to say. There is one interesting part, however. If you assume that the potential is compactly supported, then the error term, so what do we expect here as next order? This goes like, let's say, 1 to the n to the 1/3, so you expect here something of order 1, but for the upper bound we actually get something better than order 1. So this shows that the next order has to be negative. So this is just an interesting fact. So as Benjamin mentioned before, so the difference between the Hartree-Fock energy, the real Hartree-Fock ground state, and the energy of the free Fermi sea, this is exponentially small. So actually I should have written here exponentially small, as shown in work with Mathieu and David Tronfier. So let me just, so as we said, the similar result was presented by Benjamin. So now I cite these two papers in which they still assumed the smallness of the potential, but since there is a new result which holds also for basically the same restriction that like here. Now, so if we assume this condition, so actually you might wonder, this is a stronger condition than this one. So what do I mean by imposing this condition? I mean that under this condition we can estimate error terms. Yeah. But this Hamiltonian, this effective Hamiltonian, formally, if this would be bosons, for this we don't need anything on VK, we could also plug in Coulomb. So basically, this term here is more general. For this term we do not need this condition. We only need it for the error term. So therefore, when I mean under the condition that I look at this term here, under this condition, then I get exactly the term as was represented by Benjamin before. And you see that this is the KF. Yeah? And for small potentials we get the result which we had with Marcello and Felix Retsch. Yeah? So, but there is one thing I have to say, because we want to compare to physics, and at the end we want to describe the Gell-Mann-Bruckner result. As I said, we cannot do error estimates for more general potentials, but this term we can analyze even for Coulomb. And for Coulomb, this term is more general than this term, because if you plug in here Coulomb, this is not finite. But this term is. This term is. So if you plug in here Coulomb, if we plug in Coulomb, then we get this term. And the interesting thing is that if then instead we are on a torus, so if you replace this by the volume, if you add the spin variable, then this term as it's written here is exactly written in a work by Sawada, Bruckner, Fukuda and Prout, short after Gell-Mann-Bruckner, who basically did exactly the same. They looked at these pairing operators, P of P, and they diagonalized this Hamiltonian, and then they got exactly this term. And they also argued how to go from this term to Gell-Mann-Bruckner, because you see you have here basically, you have here a logarithm, and if you put the logarithm into a sum, then the sum represents all these diagrams. So they basically describe how to go from this expression to Gell-Mann-Bruckner. Now what I wrote here is the exchange correlation. So if you include Coulomb, then there is one term you have to add, namely this one. So this one is also basically on the leading order, and this one is added by hand by people like by this work. So this is added by hand because it is not represented by this purely bosonic approach, but it is, you get this term if you take into account that these are not bosons. So as a kind of first order fermionic correction, you get this term. And using the unitary, one really also gets this term. And I want to say that maybe at the end of the day, if we achieve this result for a Coulomb, we can actually teach the physicists how to give a closed expression in order to basically get in one expression all the terms where they use all these summing up all these parts. So there is let me say one thing, this matrix E of k, which I told you before, you can immediately in one line calculation or one line calculation, you get the eigenvalues. So the eigenvalues E are either eigenvalue of hk, or you get the closed equation like that. So this is an implicit equation for the eigenvalue E as a function of k, because you see you sum here over p. And so if you now replace this again with Coulomb, then you see that the k square here cancels the 1 over k square coming from here. And when you take the thermodynamic limit, you get an equation like that. And so this gives you now an implicit equation epsilon of k. And now you see, if you put here k to 0, then you have here 1 over epsilon squared times kf to the 3, and then you can solve for epsilon, and that is, this energy is what is known as the plasma energy. But this is only there if you have Coulomb. So once we can prove that for Coulomb, we rigorously established this, what they call this plasma mode. Okay, that's just for the physical part. Now for a short, let me just for a short moment come back to the low density part. And so for the low density part, you have different terms which contribute. And so this is the kinetic energy. Then this is the quadratic, basically, term in the B's. And then, as I said before, this is one term which has to be included to scattering, because this behaves like the B star, BB term. And so now you can basically follow that what Benjamin and co-authors did in one of the papers for Bose-Einstein condensation. Or I just want to mention that because so I was basically about this Bogolubov transformations for bosons. I tried also to understand that, and at the end I also wrote a little paper about that, and had a little bit a different view on it, which maybe I just want to tell her here. Namely, so this is, you can think of this is quartic, so you cannot diagonalize it exactly, but you can diagonalize it in first order. By doing what? By looking for a Bogolubov transformation in such a way. So now you do Duhamel. So you do Duhamel in, so H1 is this kinetic energy, Q2 is these 2 B's, and Q4 is because morally these are 4 B's. So you do Duhamel in this term separately and in this term separately. So doing it in this term, you get this next order, that one, and then you get this term where you have 2 B's and the general exponential. And for Q2, I only do it once here, and this is the next term. So, and diagonalizing to next order, I mean that you choose now your B so that this is almost 0. Of course, almost means apart from higher order. So I require this one, and then you get the equation for B. And then you use this, for example, now you can use this, plug in here, and then you get an expression for that thing, because now you basically solve for B, and this gives you, if you know, this gives you something like the scattering length. And morally, so when you do that, when you do this and you make this ansatz, then you get the scattering equation. You get the scattering equation, which is known in the physics literature under Bethe-Goldstone equation. And this is almost the same as the usual scattering equation, because when you put here P and Q equal to 0, then you basically get the usual scattering equation. So F is just 1 plus that. Usually you choose minus. In my convention it's plus, but it doesn't matter, it's just a sign. So it's basically a more general scattering equation where you basically exclude, here it is hidden that P minus K is bigger than Kf, and also for Q, and Q and P is inside the Fermi ball. Now if you plug that in here, if you plug this in here, you get the kinetic energy of the Fermi ball, you get the scattering length times rho square, and here you get the higher order. This is hard to get, but you know, you look in Vetter-Walecka and they explain you what this expression is. At least this is true for hardcore, but I would guess this is true in general. But you can follow their calculation easily. So now this is just, you see, this is just saying how we would choose B, but of course then you have to prove something, and that's something we did not do so far. I just want to give you the physical picture. So what we did in the first work, which I didn't mention here, but I mentioned at the beginning, we basically showed that the energy per volume in terms of density is given by the kinetic energy of the free Fermi gas and the scattering length times rho square plus higher order. So this higher order can be made more explicit, and actually if we use that, then we can improve the bound. But I mean, the goal is to do more. And of course, we are not the first one who is proving that. That was done by Lieb, Sayringer, Soloway, who also included, for example, hard sphere. So now our goal was basically to use these Bogolubov rotations to recover the thing, and to basically give a new way or a new method how to approach these systems. And I think this approach is promising. I mean, you know, you have lots of terms to estimate, but I think this is a promising way. And I mean, maybe people should look at these systems, maybe on other systems, maybe phonon interaction, or also in superconductivity, or maybe also in other parts. So that's basically my message, and I think I'm done. Also, I don't even have a thank you slide, so okay. So let's say thanks, and now I'm the last one, and I guess I'm on time, although it's already 6:30.
Thank you very much. Are there any questions?
So, one question about the asymptotics of the ground state energy in the mean field case for the Fermi gas, right? You had this theorem where you did assume that V hat was summable against K, right? But then you sort of said that, first of all, the first term doesn't need that, it's finite, even more singular case. But did you investigate under which sort of weaker condition on V the first term is still larger than whatever the error term is? So how singular can you make V so that this is still the main term?
No, this is what I said. This is what our main goal was at the beginning, to not use mean field. But our problem for not doing that was because we couldn't handle the number of. So you need to have so as Benjamin mentioned at the beginning, you need to have some a priori bounds. That when you look at your state, you're looking at that the number of particles you create here around the Fermis is not too high, and this we couldn't do for more singular potentials. So I'm just, and not even, you see, the problem is also that it would be even nice to say that if you start here, that you really get exactly for Coulomb, Gell-Mann, Bruckner, but even the fact that they are not fermions. makes also the error terms from here are you need to handle the number of excitations you do. So if they would be exactly bosons and that is Coulomb, then you're fine, because then this term is just like I said in this 4 authors paper by Prout and Bruckner and Zawada, but yeah, unfortunately not. So if anybody, so basically our goal was to give us closer to Gell-Mann-Bruckner. So for that one needs to understand how to give a more general estimate on the number of excitations. Niels, you wanted to ask something?
Yes, on the exchange term.
On the exchange term, yeah.
Right, you were mentioning that this term is also relevant for,
Yeah,
for the Gell-Mann-Bruckner formula for Coulomb, right?
Yeah.
I think it's clear if you think that you can expand the Bogolyubov transformation, the U, in a power series in V hat, it's clear that you have to get this term from this transformation. Well, are you saying you can control this at least for an upper bound, this term? You can.
No, I mean, I'm saying that when you do, so I'm saying, what I'm saying is that when you do, when you look at this, yeah, and you use this transformation, you get also the exchange term, but I cannot tell you that the other terms are smaller. I just can tell you when I expand that this is exactly this term. I mean, you can identify, but this is the same problem. If you were able to estimate the number of excitations, then you could do that. So for an upper bound, what prevents us from Coulomb is only the number of particles.
But to get this term from expanding the Bogolyubov transformation, you just do a power series expansion of the Bogolyubov
but then you have higher orders, and then you have to control the higher orders, and this is a problem.
Are there any further questions? Maybe from the online audience?
All clear is removed?
I have a silly question. There is something that I didn't understand. So at one point you said that for Coulomb there are some terms that you can control with the method that you have now and others no.
No,
is it correct or I misunderstood?
No, I said when you plug in here Coulomb, when you plug in here Coulomb, then this term makes sense. This is finite, and this gives actually this is in this term. For Coulomb, it would be Kf 3 times ln Kf. So this is rho log rho for Coulomb. When you plug in your Coulomb, I just made the argument that when you put in Coulomb here, it's not finite. But this is. And you know.
It's still you are saying that is a formal, even only for this term is a formal argument.
No, it's not a formal argument. This is finite if you put in Coulomb. There's not a formal argument. You get an expression. You can even the only thing you need to look at the literature. They explain to you exactly that this behaves like Kf3 and ln Kf. Exactly. I mean you can follow that or you can think of yourself.
Any other questions? So if not, then I would say let's thank Christian again.